Alright, hello! How's everyone doing today? Welcome back. We're going to be doing another video and pick microcontrollers. It's going to be a back to basics video here. I had a fellow viewer bring it to my attention that we have never done anything with 7-segment displays, which 7-segment displays are definitely a basic component, one which everyone should have. It's a good way of displaying what's going on. What we're going to do is we're just going to do a counter, so just going to count from 0 to 9 and back to 0. That's what we're going to do with a 7-segment display. Alright, so to jump into this, get into the hardware of it, we got a good old 16F676. I like these little chips. They're inexpensive and they're easy to get your hands on, readily available. We're pulling this up. I didn't go through putting a regulator on this and all that fun stuff and showing all the decoupling capacitors and all that jazz, so I just left all that off. If you want to see what I'm talking about, you can just kind of watch really any one of my videos on just how, on how to set up a PIC microcontroller. Even the Blink video, I believe, has all that on there. But so for right now, this is just a simple setup of how we're going to do this. So we've got our 10K ohm memory pull-up. The reason I use that is because I use a ICD, which is in-circuit serial debugger, or ICSD, I guess you would say, but it's an ICD. It's an in-circuit debugger. What it is it's a device that wires into the actual chip while it's in the circuit and programs it, debugs it, does all that stuff. So you need the external memory clear pull-up, so that way it can toggle a soft reset. All you gotta do is grab it right here, pull it to ground, and it'll toggle a soft reset of the PIC microcontroller instead of just pulling the power on it. So anyway, and it does that when it reflashes the memory, or the program EEPROM. So anyway, so we got that all set up. We're going to be using 4 data lines. What I'm going to be using is one of these 4511Ds. Now, those of you that don't know what this is a BCD to 7-segment display or whatever, converter, or just one of those drivers. If I remember right, I have, there it is. The one that I have is the HEF4511B. It's the BCD to 7-segment latch decoder driver. What this little guy does is it allows you to index it using binary coded data, or BCD. BCD does is that's that 000 is 0, 001, 002, or 001, 0011, 100, 101, 1, so on and so forth, using binary code to actually increment it in binary numbers is what you're going to do. Makes it very easy, since this one is a common cathode, is the way we're doing it. Let me sit and let me show you. Oh, get this on out of the way. So what we got going on here, see, we've got common cathode, which means the cathodes for all these are all kind of like put together, and all the cathodes are tied together and brought to these 2 pins. So I'm just bringing those to a ground, and then obviously the anode, because remember these are LEDs that are in here. What's inside? There's just a whole bunch of them. There's 8, 9 counting the little whatever it is, the little decimal point, LEDs that are inside here, and they all have all their cathodes tied together and brought out to these 2 pins, which I'm just bringing to a ground, so that way we just apply power, and that's how it works. So we're going to be sourcing, not sinking, and that's what this little driver chip does. So essentially it has latches, a decoder, and drivers in it that does all this. So you basically take in 4 data lines, so you can put numbers 000 to 111 to 1111 is basically what you get in binary, and then that selects or that enables the decoder to decode and select the right digits for you. We'll see that later on in this data sheet. As you can see, there's all the latches, the decoder portion, and all that fun stuff. We'll get into those other pins here in a minute, but see, here's your decoding. Here's the truth table of it, and that's how it'll actually by giving it like a binary 0, it'll light up segments A, B, C, D, E, and F. By giving it a binary 1, so basically 3 zeros and a 1, 0, 0, 0, 1, going from left to right, you will get B and C will light up for the number 1, and so on and so forth. If you give it a 0, 1, 1, 1, which is 7 in binary, you'll get A, B, and C, which will give you the 7. Okay, so it's actually pretty darn nifty little device. Otherwise, you would have to, program in all these different numbers as to which LEDs are lit up into your microcontroller and all that fun stuff, and so it would just be a lot more code. This makes it very easy, and you'll see that when we get to the coding portion. It makes it very, very easy. So what we're going to do is we're going to go back and I'm going to show you those other things. You've got, let's see, where was that at? Okay, here we go. You've got these LT, BL, and LE. You've got a lamp test, which basically if you yank this low, it'll just light up everything. So it's a lamp test. It'll just output all ones on everything, so that way it'll light up your LED things. It works for like if you want to on power up, let's say, check all the lamps by giving maybe a 2 or 3 second lamp test by turning that on. You can do that with this pin. Also, the ripple blinking input, active low, I believe that's if you want to like PWM this thing. I don't remember, I haven't read through this data sheet, but I think if you want to PWM it, to try to save the life of the LEDs, so you're not just powering them fully on, and two, also you can save some power by running a PWM wave. That way you get kind of more of an RMS current than just a full-blown current coming out. So I believe that's what that's for, is that's a ripple blinking input type of situation. Then you have a latch enable, which the latch enable is basically as you are changing it around, so as you're changing these numbers around, your micro could be, I don't know, incrementing them, or who knows, but as you're changing these around, you can inhibit the input so this logic doesn't get, you aren't like changing stuff around in this logic. You can actually take and clear the latches and hold them in clear while you're shifting data around on the input, and then you can let it go on through. It's kind of similar to those parallel to serial and serial to parallel converters, those 595 and 597 chips that we looked at in previous videos. Kind of the same thing. So we'll be using that latch enable to basically shift our data. Once we get it right, we'll shift it in to then decode it and bring it out. So that's essentially the decoder. Fairly simple. So that's basically what we've got here. We've got that those two pins, that blinking and the lamp test, all brought to a high because they're active low, hence why they got the little circles, which means they only activate when you yank this line low, which we're not going to do for this instance. Now if you wanted to, you could take one of your empty pins over here, pull it over and hook it in, let's say for the lamp test one, hook it in right here, and then just give it a 1 all the time until you want to do a lamp test, then just give it a 0, and it'll pull this down and it'll actually do the lamp test and output all ones over here on the output side of the registers. So anyway, so I went ahead and did the latch enable. So the latch enable pin is on RA5. That's where that is. And then I've got, and this is important, I used port C, and you'll see why I wanted to use the port. What I'm going to do is I'm going to show you how you can actually stretch. You can give a number to a port instead of actually constructing the binary number yourself and then issuing that to each and every pin. You can actually put the entire number to the port, and the port will just write it out. Now, the LSB and MSB on it's on these, it is, and I don't remember what indices that is, whether it's big Indian or little Indian. I think this is big Indian, but I'm not sure. Don't quote me on it. I'd have to go look. It's been a while since I remember which way was which. But it's basically you're reading it from right to left. Okay, so your right to left. Your right is your MSB, your left is your LSB. Okay, and those of you that know, MSB means most significant bit, LSB means least significant bit. Okay, FYI. Anyway, what we're going to do is I've got C0, and I did this, and I made sure these were the same. C0 goes to A, C1 goes to B. So you want this to be in order from 0 goes to 0, essentially 1 goes to 1, 2 goes to 2, 3 goes to 3, okay? So that's how you hook this up, okay? Because this order does matter as we're doing this, if we're going to do this whole port thing. Now, if you plan on literally assigning each and every pin, you know, having you say, hey, this in this case, this one's a 0, this one's a 1, and this one's a 1, and this one's a 0, or whatever you want to do that you know, that's totally fine. But for a counter, it's easy to use this neat trick where you just output the output to a port and just go that way with it. So anyway, that's basically the hardware. Not too difficult. This driver chip is awesome. Notice there isn't any resistors in here. That's because this driver chip takes care of all the current needs and everything for this guy to make sure it doesn't overpower it or hurt it in any way. So yeah, pretty simple setup. Just 3 resistors and a couple chips, and there you go. You got a driver circuit that you can program a micro and do whatever you want with it. So pretty easy. I'm going to go ahead and go into the software because the software is very simple for this. So let's go take a break. Let's grab the software. Oh, have to log back in here. And here comes our software. So now for our software, we just went ahead and configured some, you know, our normal registers, our crystal. Now this is, I'm going to configure this as our strobe. What this is going to be is, remember that latch enable pin that I was talking about? I'm just going to configure just like we do for LCD screens. If you don't know what I'm talking about, you can check out some of my other videos where I did LCD screens. We're going to use the strobe way of doing things, where you just kind of make a defined statement, and we're going to define kind of a quick like function. And we're going to take RA5, bring it to a high, delay a couple of cycles, and then bring it back low. Okay? That's all this is doing. Then I'm going to call this count. This is going to be our function that's going to count up. And so what we're going to do is we're going to declare ourselves a for loop. And this is where you do it. You literally type port C, or if it was port B or port A or whatever. Now on a 676 chip, you only have A and C, but if you had a bigger chip that had A, B, C, D, E, you know, whatever port it is, you're going to type port and the port letter, and then equals, and then just type the number, and it will literally output. It converts the number to binary if you type it in decimal or hex or whatever, and it literally outputs it using the RA port 0, 1, 2, 3, or RC port 0, 1, 2, 3, 4, 5, or whichever it is. It literally goes that way. The port 0 is the MSB, and then to whatever, if it's 5 or it's 7 or however big however many pins are on the port, that will be the LSB, and that's how it defines the binary numbers. So pretty darn slick. So what we're going to do is we're going to output our number, and then we're going to strobe our latch enable, so that way it goes to the output. And then for me, I'm just, since this is going to be like a quick little counter that's just going to count indefinitely, I just delayed it 500 milliseconds, so that way you can see it change. Down here in our main function, I made sure, and on the 16F676 chip, I had to set the analog select register, which sets whether or not pins will be analog inputs to the ADC, or if they will be all digital input outputs. And well, I want them all to be digital I/O because I'm not doing anything with an ADC. So I set that to 0x0, which 0 is for digital, 1 is for analog. So that sets all of the analog register, or all those pins that are associated with the ADC, to digital I/O. So it sets them all to GPIO. Then I'm going to set up our tri-state buffers, essentially our tri-state things for A and C. I'm going to make them all output, none of them input. 0 is for output, 1 is for input. Then what I'm going to do is I'm going to initialize things. I'm going to take port C and initialize it to 0. Then I'm going to take port 5 and initialize it at 0. And then guys, all it is set up our infinite for loop, or you know, in video game making, it'd be the render loop. But basically set up your main loop and then just call that function, and it will just count up, and it'll roll over. It'll count up to 0 and then roll over, because obviously this function ends executing, and then it just calls it again. So yeah, pretty slick, guys. Not too difficult at all. And you can put 2 of these in, and then hook up code to where when one rolls over, it calls the next one, and so on and so forth. You could get real creative with this. So guys, I think that is probably going to be the end of this video. It's hopefully it wasn't too terribly long, but like I said, I just wanted to touch on this because I had a viewer that mentioned I hadn't done it, and I just thought, oh, I haven't done this yet. So there you go, back to basics with a 7-segment LCD and a BCD to 7-segment display converter chip. So guys, if you like what you saw, drop a like, subscribe, share, all that fun stuff. Check me out on Twitter, Zazzle. I even got, since the spirit of all the holidays are coming, I've got some really cool stuff on the way for you. Even some Christmas stuff. I think we're going to do a Christmas video this year. I hope you guys enjoyed the Halloween video. I enjoyed making it. It was a lot of fun. So I hope you guys enjoyed all that. All that jazz. I think I'm out of stuff to say. I'm going to start rambling now. So guys, take care. Keep coding, keep building, keep having fun, because that's what it's all about. And with that, guys, that ought to do it. Take care. We'll see you next time.